The purpose of this video is to go over the continuum that CSAT's adapted from the Instructional Leadership for Science Practices program at Boston College. There are many similarities between the engineering practices continuum and the one for science practices. This was done intentionally. However, we also want you to note the differences in the practices, as it will likely be important for you to understand these distinctions and consider how to support your students' engagement in them during the classroom research project that you will develop as a part of the CSAT's RET program. As we have already discussed in the week 3 session, of the 8 science and engineering practices that are listed in the Next Generation Science Standards and Framework for K-12 Science Education, only 2 of them are distinct to engineering: defining problems and designing solutions. As we have read in the Cunningham and Kelly paper, some have proposed that there are several more practices that are both unique to engineering and relevant to the K-12 classroom, such as balancing trade-offs between criteria and constraints and persevering and improving from failure. However, it is also important to understand the ways that the NGSS practices differ based on whether the practice is part of science or part of an engineering project. The primary reason for these differences are based on the fact that the goals of science and engineering are typically very distinct. The purpose of science is to figure out how or why a phenomenon occurs. Usually the audience of a scientist's findings is the whole field, or mankind in general, as the overall goal of science is to better understand the natural world. On the other hand, engineering is typically intended to develop technology, which is a product, system, or process that solves a problem or makes life easier. Like the diagram for science practices, this figure breaks down the practices into 3 groups too. In engineering examples, problems lead the engineers to engage in the designing practices, which creates data. Those data are analyzed and eventually solutions are developed or improved. A key difference in engineering is the justifying practices. The consumer of engineered technologies are typically a client or an end user. A key aspect of communicating with the client or end user is the justification of the solution as being the best design given the criteria and constraints. In order to go from problem to solution, data is required. That data is used to analyze the effectiveness of the design, used to compare multiple design possibilities, and it's used to consider the effects of modification of one aspect of a system on the total system performance. Defining problems also often requires feedback from a client or an end user. It is within this practice that the criteria and constraints are determined, and the engineer can determine what a successful design entails. Planning and carrying out investigations is used to measure the effectiveness of the design and compare against multiple solution ideas. And this process of getting data involves using math and computational thinking. The analyzing practices are how an engineer either gets from the gathered data to inform the solution. As you probably understand, this representation of the practice is not intended to suggest that it's a linear or stepwise process, as the analyzing practices can often inform the engineer to go back to the design practice. However, engineers use models to analyze data. Obviously, analyzing and interpreting data is found in this set of practices, and so is the use of mathematical and computational thinking. Scientists engage in argument from evidence to persuade the field that the work that they have done has merit. However, in engineering, the field is rarely the audience. Instead, engineers argue from evidence as a way to justify their design as being the best design given the particular context. However, engineering is typically a collaborative affair, and argument from evidence is also found when working on these teams to suggest other alternatives or to change the criteria or constraints. The engineering practices continuum was developed to help teachers think about what it would look like for their students to participate in the engineering practices and to give them a tool to assess this participation. This continuum in table form is arranged such that the designing practices, the analyzing practices, and the justifying practices are grouped together. Generally speaking, the level 1 category suggests that the practice does not exist. As we have mentioned previously, the goal of every activity in every class should not necessarily be to engage every student in level 4 practices. But as you go from left to right across the categories, the practices tend to be focused on design, more student-directed, and more collaborative. And another key indicator of high-level practice is an emphasis on improvement over a number of iterations. Sometimes it is appropriate for a number of reasons to want to engage your students at level 2 or 3. However, we should keep in mind that level 4 is where we want our students eventually to get, but we should work in that direction whenever possible. Let's use the example of our trust activity to discuss two of the practices in the engineering continuum. One of the practices you all engaged in was the use of models. You used both Maston as a way to analyze performance of the members and to examine the forces exerted by each. You also used the decision criteria tool as a mathematical model to compare a number of iterations of the trusses and to compare how they minimize cost, mass, and deflection. The fact that you did not create the Maston simulation or the decision criteria tool does not mean that this practice was less than level 4. Another practice you engaged in was the use of mathematics and computational thinking. You did this when comparing the different iterations. However, in the trust activity, you did not make decisions about which skills or concepts to use. As the designer of the lesson, I used math and computational thinking when trying to figure out a way to compare units that were orders of magnitude different. For example, deflection was measured in tenths of an inch, cost in thousands of dollars, and mass in hundreds of grams. I included an importance factor to make the three variables roughly equally important. However, it was a decision made by me to involve you at the level 3 because it was going to be much more time effective and efficient if you participated at level 3. As you start to develop your classroom research project, it will be equally important for you to think about which of the practices your students will be engaged in, and also for you to decide at which level they should be engaged.